And so let me open the tutorial questions today. Okay, so can you see my tutorial question?
Yes, sir.
Yes. So today is really based on the same lecture because we missed, like there was during the exam day, we could not do on lecture. So there are how many questions here? There are one question on the quantile regression technique. We have been given some equations here, and some data is given in this table, and we have to estimate this 2-year, 5-year, 10-year flood quantile or design floods for this catchment, which is Unjela in eastern New South Wales. It has latitude and longitude given. So this is based on Australian rainfall runoff 1987 version. So now the second question is that we have to apply the probabilistic rational method for the same question, and we have to use this equation to estimate our flood quantile, and using this data in this table and in this table as well. And a contour map of C10 is given here. And then we have to apply the Australian rainfall runoff RFFE model. And we have to estimate the flood quantiles for this site with this data, or we have the latitude, longitude of the centroid and the outlet of the catchment. And we have to present the results of the flood estimation. So these are some of the output that's coming from the software. Okay, so let us start one by one. So first question is our data is given here. So the best thing is that it's a good idea to set up this in Excel so that you can do all of them together at one go. So can you write down these equations so that you can go to Excel? And do the solution. I can do a screenshot like the sniping. So let me use sniping tool. So use sniping. So I'll take this part. Control C, and then go to our Excel. Let me stop share this on, and then let me open an Excel file. So share a screen and then go to Excel file. So you can see the Excel file, is that right?
Yes, sir.
Okay, so basically we want to estimate our, so that is our T or return period. And then return period is changing from 2, 5, 2 year, 5 year, and then 10 year, 20 year, 50 year, and 100 year. That is our return period in years. So T in year. So let me create some solid border that will be easy to see for us, and then everything make it as in the center. So that is our return period T. And you see here the equation that for each of the equation, we have a coefficient, and which is different for different quantile. So for the Q2, we have minus 3.46. So let us tell this is our B0 coefficient of the regression equation. And for 2 year, it is minus 3.46. 3.46. And for 5 year, it is minus 2.73. For 10 year, it is minus 2.33. And for 20 year, it is minus 1.99. For 50 year, the coefficient is minus 1.58. And for 100 year, it's minus 1.30. So these are our B0. And then we have number of other coefficients, which is our B1, which is related with area. So we have to write B1 here. So our B1 is 1.25. And then 1.15. Then 1.09. And then 1.051. Or 1.051, not 1.05, so 1.05. That's one, it's log. And then we have 0.99. And then we have 0.94. 0.94. So that is beyond. And then we have our catchment area. A is our area of the catchment. And what is the area of the catchment for this problem? The area of the catchment is 213 kilometers square. So 213. And that is same for all the return period because area is constant here. Area is not changing. Catchment area does not change the return period. And then we have the coefficient values, which is our B2 or second regression coefficient. And that is changing from 2.40, 2.10, 2.40, 2.10, 1.94, and then you have 1.78, 1.78, 1.59, 1.48. And then we have our ITC T value. So that is our rainfall intensity for TC duration, time of concentration, and our T. For different T, it will be different value. So this rainfall concentration intensity for different return period is given here. ITC 2 is 17 millimeter per hour. That is obtained from Australian rainfall runoff This is the old version. So this data is not nowadays available in the website, but really this is the past data. But anyway, the data is given here. So which is 17 millimeter, 22.6. 17 millimeter, 22.6 millimeter per hour, 26.10, 30.6, 30.6, and 36.7. And 41.5. 0.5. So these are our rainfall intensity. So this is our area is in kilometer square. Kilometer square. And our ITCT is millimeter per hour. Okay, so now we have set up everything. Basically, now we can find out that our log 10 QT value. First, we find that, which is basically equal B0 plus B1 times area of the catchment, B1 times log 10 of the area of the catchment. So log of 10, and the area of the catchment is here. And then plus our B2 times log 10 of our J49 cell. J49 cell basically. So that is our log 10 QT. So I can copy that directly because I have created the formula in such a way that it's linked with all the cells. Then now I can find out QT here, which is 10 to the power of this value here. So that are our answer. That is the QT value for different return period, and we can draw that in a flat frequency curve. Like we can select that return period and then this.
Sir, excuse me.
Yes.
So what is the unit of the flood value? Because like once in millimeters and once in kilometers.
This is meter cube per second, because when that is an important question you have asked. When you develop this kind of regression equation, then the equation will tell you the unit, because these are regression equations. They are approximate equation generally. So it is not like a mathematical equation. It's like it's a curve fitting procedure. So in this case, you need to know what is the area of this A, which must be in square kilometer. And the unit of ITC10, it must be millimeter per hour. And if these are the correct units, then, and if the T is in year, then the flood that will be estimated will be meter cube per second.
Thank you, sir.
So this is called a non-homogeneous equation. In fluid mechanics, we discussed some some types of homogeneity in there. So this is called dimensionally non-homogeneous equation. Okay, but that is a good question. Okay, so we can plot it. So we can insert, and then we can go to here, and then probably we can select some of this curve here like this. So in this curve, of course, we have to select the axis. So the axis title. So this axis title here is our return period T in year. And our y-axis title is
booked for Saturday.
QT.
So
that is in meter cube.
After work, just go to the PCYC.
So it's really, instead of QT, it's better to say, in my opinion, Q. Because once you
So you know the
develop
place
this
that my
car,
dad booked with?
because you have access already there, so I would say Q
No, like I'm saying that he booked with them.
per second.
We go there and she goes, Pfizer, Astra. He goes, I already made a booking. She goes, yeah, all right, but Pfizer, Astra.
Can you stop
Because
talking? Somebody's
Pfizer-
talking. Can you mute yourself? If you are not talking, please mute yourself. So now this is the flat frequency curve at that location, and we can make it log axis. So we can go to format axis, and then we can select the log axis here. So it make you linear, kind of more better curve in the sense like it's become a little bit linear. So this is the flat frequency curve for that side according to the QRT method. So this is the, in the title we can say this is the QRT, quantile regression technique. So do you have any question on this problem? Anybody has got any question on this?
Sir, on the x-axis, the scale is for return period T. So it only
Yeah.
shows 1, 10, and 100. So is it possible to show more than this?
Yes, possible. Like you have to add the minor axis level. Like I think you can go from here that the maybe under the design something there is right. So under Excel chart design, so you can show the axis. No, not that one. You have to go for minor axis.
So if you press the plus sign on the top right hand corner of your graph, and then
grid
yeah,
lines,
grid lines,
and
and
under
you
the
can-
grid lines, you can
yeah.
show the primary, minor, vertical. Yeah, that's right. So it's here. Like different version of Excel has different way. Previously, it was something different way, but now it has. They have really it has given everything here. Basically, you can see here axis titles, chart title. You can do the error bar. If you press the error bar, then it will give you an error bar of the estimation. And then, of course, you can put a legend and then add a trend line there, but we don't want to do that. If you want to do a trend line, then really we don't want to do that here. So basically, so this axis is called log axis. So you can say if it is 100, then this is 200. If this is 10, then next one is 11. If this is 1, next one is 2. So this is called the logarithmic scale. Any more question on this? Okay, so that's good. Okay, now we will go to the next problem. So I'll stop share this on, and then let us see the next problem. What is the next problem? Okay, so I'm going to share my this on here. So the next question is, for the same location as provided in question on, apply the probabilistic rational method from Australian Rainfall Runoff 1987, book 4, page 2, which is the old version of ARR, and obtain design floods for 2, 5, 20, 10, 20, 50, and 100 years return period. average recurrence interval. Compare the results obtained in this question above, and like we have to compare the question 2 and question 1 results. Comment on any differences in the results by the two methods. Note that y equals t equals ARR equals return period, same thing. So the equation is given like this. QY equals 0.278 CY AITCY. So that is the equation that we have to use. And we have to, the frequency factor is there. So you can see that for 10 years, frequency factor is 1. And then you are multiplying with a higher number to make it higher return period. And to go to a smaller return period, you are multiplying with a smaller number, a smaller factor less than 1. So 10 the benchmark, C10. So in that case, what we can do, we can estimate Q10 flood, Q10 from that equation, and then we can multiply with this frequency factor. So, and the design rainfall data is given here for different return period as before. So let us, let me copy this thing, and we'll go to Excel there again. So these are the frequency factor. So we need this data. So I'm going to Excel. I'll show you Excel later on, but we need a few more information from here. So we need our this equation here, that QY equals this equation. We have to apply this equation as well. So let us do that, sniping that equation here as well. The PRM is represented by this equation. Control C. So Control V. I'll show you Excel in a second. And we need the C10 value, and C10 value has to be obtained from a map is like that. So Australian rainfall runoff 1987, they produced a map of the runoff coefficient. So in this map, it has a latitude and longitude. So you have to locate the outlet of the catchment on this map. So in this case, this latitude and longitude you find at that point here. And the C10 value has to be estimated by the two nearby control line. So the two nearby control line is, one control line is this, which is 60. You can see this control is 60. Because our location is this. So there are two contours, one contour here, another contour is there. So one contour is 60, another contour is 80. So there is between two contour lines, 60 and 80. And it's really kind of in between, the middle, kind of in the middle. So you take a average of these two, so 60 plus 80 divided by 2. This is a linear interpolation. So this is one of the problem with this technique, that you can see that the density of the control line is quite not that many control lines. And when you want to do interpolation, it's really a lot of uncertainty there. And so in this contour, drawing this contour map also has a lot of uncertainty. And then there is another level of uncertainty in interpolation as well. So, and different people will come up with different answer, because it is a bit of subjective, that whether it's in the middle or on third or something. So all this really make this technique a little bit subjective. So do you have any question on this contour map?
So can you explain how we got the C10 again?
So based on the latitude and longitude of the catchment, you have to locate that point in this map, which has the latitude. You see, this is the latitude, and then we have longitude on the other side. So based on that latitude and longitude, I am locating my catchment at this location here and this here. Okay.
Yes, sir.
Then I have to see what are the control lines in between those 2 points. So I can see that one contour is this, is that right? That contour has a value of 60, you see here? 60.
Yeah.
And then we have another contour line here, which is 80.
All right. Yeah.
80. So then I am assuming that my catchment is in the middle of these 2 contour, which is my assumption. And then you are taking the average because it's in between the middle. If it is 1/3 distance, then you have to interpolate accordingly. So it will be more closer to 80. Okay, so I think it's clear to you this contour map. It is available in the ARR 1987 version. This map. Anyway, so now we can go to the my Excel sheet. So I'm going to share with you now the Excel sheet again. So can you see this Excel?
Yes, sir.
You can see this Excel sheet, is that right? Okay, that's good. So we can see that our QY, if we want to estimate our QY or QT, in this case, you are telling Y in ARR, they told it Y. So we see that we have, so this is our Y value. So our Y value is 2, 5, 10, 20, 50, and 100. That is our Y value in ER. And then what I'll do, I will a little bit higher here. And I'll create some column for my calculation purpose. So that is my Y, and then this is my CY. CY, so our C10 value is given. So what is the C10 value here? That we estimated from our contour map, which is 70. Okay. And then we have a frequency factor, which is FFY. The frequency factor for 10 here is 1. And then we have the frequency factor for other return period in this table here. So we can see that it is 0.81, 0.92. And for 20 year, how much is that? 20 year, it is 1.07. 1.07. And then 1.33, 1.50. 1.50.
We're sorry, sir. Where do you get the 70 from for CY?
The 70, we got it from the contour map. The contour map that I was showing you before, that is the contour map for 10-year return period.
Okay, gotcha.
So they have only one contour map, which is for 10 years, and then for other C10 value, you have to multiply that C10 with this factor. So that is the C10, is that right? So for other return period, our CY value would be basically this value times the frequency factor of that particular return period. So that would be the CY value for other thing. No, I think I have done a mistake here because I have not used. So this is really just that times this value. Yeah. And similarly here, it will be this value. I can make it absolute reference by pressing by putting a $ before F here and a $ before the cell. So I am fixing it. and then multiply that value with, so multiply that with this. So I have fixed that, and then I can multiply that with this, and then I can do it for all of them.
No, sir, copy the for 20. Copy
Up to 20, and then here I have to do it.
yes.
I have to really, I have that F fixed, and then G7, so which is G47. Let me see what's happening. So here I have G47, here should be G48, that's right. Here should be, again, it would be G50. Yeah. So these are the runoff coefficients for that particular value. Like I can double check it by multiplying that with this value. 150, so that's right. My calculation is right here. But you don't have to do the equation format or something. You can do by your own way. That's fine. So you got the FFY, and then what we need in this equation is that we estimate our QY. We need a coefficient. So, and then we need a CY. We have done CY already, and we need our area of the catchment. So, what are the area of the catchment for this case? It was 233. Is that right?
Yes, sir. The same catchment 233.
The area of the catchment is 213. Same catchment 213. So our area is in meter cube per second. No, sorry, area is kilometer square. Right? So that is our area, and then we have to find out the rainfall intensity for different Y and TC. So that value is given in this table here. So ITC2 is 17. So ITC T value. So it is for 2 year, it is for 17 millimeter per hour, then 22.6. Then 26.1, and then we have 30.6, then we have 36.7, then we have 41.5. I'll show in a minute how to get this value from Brewer Meteorology website.
Sir, should we write the J column title ITCY or instead of T?
I think you're right. We should write UI here because we are using ARR old version. So millimeter per hour. Thanks for mentioning that. So we have to use Y. You are right. Okay. So is that clear so far? Then we can find QY now. So QY, according to this equation, it would be meter cube per second. So now I will apply this equation, which is 0.278 times the coefficient times CY, we have done it here, times our area here, times our ITC value, which is I47. So I just type I47 here. So there is a issue here that many people that do this mistake is that this CY value is really in percentage. So it really, we have to divide that by 100 if we want to use in this equation. So basically when I am doing this thing, then I have to really divide that by 100. So that is our QY for different return period. So how was the value in QRT? We have to compare these two methods. So our this method was like this. So let us copy this and come to this sheet here. So this is the QY with the which technique? PRM, probabilistic rational method. And this QT which technique? It is QRT, is that right? Any questions so far? So you can see like really we can see the big difference, is that right? So you see like we cannot copy in that manner.
Value only value.
So we have to copy only the values. So basically if you go there, Control C, then come here and then right click on the button and they only say values. So you can see now that really, and it's a good idea to make up to 2 decimal only, not too much. They are not very accurate. So make up to 2 decimal only. So we can find out the percentage difference by 2 technique. So say this is our QRT minus PRM divided by PRM times 100. So what can you comment on the result? Is Tanzim here? Tanzim? So can you make a comment on the results by in comparison of the 2 techniques?
So as per my understanding, I would like to say between these 2 methods, probabilistic rational method can overestimate or rather compared to the quantile regression method, and it is around 55%. More.
Oh, that return period for 2-year return period is 55%.
Yeah, for 2 years return period, yes.
And for 20-year return period is 7%.
Yeah.
And for 100-year is 25% difference.
Yeah, almost 26%. Yeah.
So because we don't know which was is right and wrong, because this is unguessed location and we don't have the data to verify it. So really, if you use different technique, you will get different answer. And then you have to make a decision based on that, the design. So in the exam time, if we say that really make a comment on this result, then you can say that in this case, your PRM estimation is higher than the QRT for all of the quantiles. And the difference is the most for the 2-year return period and the smallest for 20-year return period. And it's ranging between 7% to 55% variation between the 2 methods for different return period. So any question on this?
Can we make one comments here like the less the return period, the uncertainty is more?
It's not uncertain, it's a difference between the 2 methods because you don't know which one is correct.
Yes.
You can say difference is more for a smaller return period.
Yes, yes.
But again, for the high return, it's increasing. So there is no pattern in my opinion.
Yeah.
So during the lectures, you said the PRM method is like not used anymore or something?
That's true. That's true. PRM is used not anymore, but still many councils and engineers, they want to compare the RFFE result with this PRM. because PRM has been used since 1987 to 2016. So around 13 plus 16, around 30 years time, people have used this PRM to design numerous infrastructure, numerous bridges, culverts, and so on, thousands of them throughout whole Australia.
So if we were to design something, what would you recommend to use? Which method?
Currently, you have to use ARR RFFE model, which I'm coming next. Because
Oh,
this is
alright,
no
sir.
longer recommended.
Thank you, sir.
Okay. Any other question? But in your workplace, most of the time, the people will ask that compare your results with the previous technique, PRM. So that's why it's good to know both the techniques. You need to know both the techniques. Is there any more question on this? If not, then I'll go to the next part of the problem. So which one you believe more accurate, PRM or QRT?
QRT.
In your opinion, QRT. Okay. Why is that?
I don't know. So I just said because it's a recommended method, higher than the PRM at the current moment.
You can say that the equation that we are using here that is developed based on the latest data, because this equation are developed by one of my honors student, James Perogi, who got first class honors and he got the best thesis award in the whole New South Wales. He did his honors thesis with me, and he was regarded the student of the year in whole New South Wales based on his thesis. And he that's a big prestige, because considering all the departments and all the universities in New South Wales, he was #1 student in terms of thesis. So he developed this kind of equation under my guidance using the latest data in New South Wales. So these equations are more reflective, because in 1987, when they developed the PRM, at that time data length was even shorter. So there's a lot of uncertainty with that PRM. So with the recent data, I think the QRT here is more accurate in my opinion, but it's very hard to say that. Anyway. Okay, so now let us go to the last problem. So can you see this question 3?
Yes, sir.
So can you read, everybody can read, can you read this question 3 by yourself? Because it's important that you really see what are the data given. So read this equation and try to solve it by yourself. And then let us see how it goes. Okay, so can you try this problem by yourself? There are some data given, and there is a link there for the software, which is ARR RFFE model. So this is the data that we have to use for that software application, which is the latitude and longitude of the centroid of the catchment. So these are the lat and long. So it's minus 30.352 and 151.936, which is at the centroid. And at the outlet is minus 30.478. And longitude is 152.026. And area of the catchment is 376 kilometers square. And catchment name is Colomboy River at Quantile. Colomboy River at Quantile. So basically, you don't need any other data. Only you need this data to apply the technique, because rainfall intensity and all other data is embedded within the software, and it is linked with the Australian Bureau of Meteorology website. So it will read the data for this location from Australian Bureau of Meteorology website. So you will find an input window like this, and then we have to enter this data like this. And then you have to say submit. So can you do it by yourself? Can you hear me?
Yes, sir, we can hear you and we can try.
Yes, sir. We are doing, sir.
So did you get the software? So this is the
Yes,
software
yes.
link.
Yes, yes, I got.
So now in that software, then enter the data and then say submit. So okay, let me share the screen with you. So share the screen. So everybody can see this screen here now?
Yes, sir.
Yes.
Okay, so this is the basic and this is the advanced. So an advanced level application. So generally we do the basic first. So you have to give a catchment name, which is our Colomboy River at Quantile. I am writing in abbreviated manner. It doesn't matter whatever you write. And the outlet location is minus 30.352, and your your 30 point outlet is 30.478. That is the latitude, and your longitude is 152.026. And then come to the centroid of the catchment is minus 30.352. And then centroid longitude is 152.026. So let me check the data again. So my outlet is minus 30.478, 150.026. And then my center of the catchment is minus 30.352 and 150.
The below one might be 151.
151.936. No, 151 point. I think I made a mistake. 151.936. Is that right?
Yeah. Yes. Yes.
That's why it's always good idea to double check the data because you can do a mistake in data entry. So and catchment area, how big is our catchment area here?
367. 376. Yes, sorry.
376 square kilometer. So I have entered all the data. So it will once I click the submit, it will use a very complex model that it will select the catchments which are nearby to that location. Now you see in the map, it's showing where is the catchment. It is really in northern New South Wales, northeastern New South Wales, and then it will take the rainfall intensity from Australian Bureau of Meteorology website at that location, and then it will do a Bayesian parameter regression analysis and using ROI approach, and then it will fit a regional LP3 distribution, and then it will do 10,000 Monte Carlo simulation to estimate the uncertainty, and everything will be done and produced the results to you within a second. So now the analysis has been done within a second, but during this time it has done at least 20,000 calculation under it. So now you can see the result here that for different AEP, 50% means 2-year return period, and 1% means 100-year return period. This is your discharge, design discharge. And this is the lower confidence limit, upper confidence limit. And these are the data that you have entered, and it is giving the rainfall intensity coming from Australian Bureau of Meteorology. And then really the shape factor of the catchment is recording here. And it's giving the correlation matrix for fitting multivariate normal distribution to develop the confidence limit. And it's producing a result. And you can see for 1% AEP's confidence limit is so wide. You see for 1% AEP, your expected discharge is 939, but your lower limit is 414 and upper limit 2110, almost double. No, that is for 1% is 3030 and 1270 is the expected. So it's really 2.5 times almost the upper limit. And then it also shows your location is here. And then it is using the data from all these catchments in that area. And you can see in the map here that this is your catchment here. And then it's really taking the data from all these nearby catchments to develop your equation and do the estimation within the background. And this is really telling you that whether your catchment has very unusual shape. So shape factor is really varying in this range, and your catchment is here. So within a reasonable range, that is not something going out of the bound of the catchments. This is the rainfall intensity versus catchment area. So you can see there is no pattern here. And this is the bias correction factor, but we did some bias correction. And then you can get the results by text format here. And you can also get the data from the nearby catchments, that what are the data for different catchments. So if we click this button, then you'll see some answer. So any question on this? So do you have any question or comment?
So like maybe comments. So when we put the data, it automatically select the nearby catchments, right?
Yeah.
So yeah. So is there any threshold that how many catchments they might be select, or it is based on the region of homogeneity?
This is really, it's doing some optimization. So it starts with say 5 catchments and then it increases, and then it sees that if the catchment 5 is not very good, and then you 10, 10, 20, 50, 20, and then it do kind of optimization. And it takes the optimum value when the error is minimum with size.
Okay.
Excuse me, sir.
Yes.
What is that bias correction factor?
Bias correction factor is sometimes, in previous case, we found that our PRM method is smaller, and our QRT estimation is higher, or say otherwise. But we saw that it's really a pattern that there is underestimating all the time.
Yep.
So if we know that kind of pattern, then we can multiply by some factor so that the difference reduces. So the difference, overall difference reduces. So that is called bias correction. Bias correction is an important area in this kind of area subject. And there are a lot of different ways you can do the bias correction. So we have implemented a particular bias correction method. You can say nearest neighbor method. And that is implemented within the software.
Okay, sir. Sir, I can see that our catchment is number 1 and is sitting close to 0 line.
Yeah.
And
so that means that for your catchment at that particular location, you have no bias, because you have raised an important question, because this is a guest catchment. Is that right?
Yep. Yes,
so
sir.
For guest location, you don't have any bias because you know the value.
Yeah.
So that's why at guest location, your bias correction is not relevant. But when you are doing it for real unguessed catchment, where you don't compare your results, because in this case, we are trying to compare the results. That's why we're using a guest catchment. But we can make an unguessed catchment, like we can reduce this latitude, longitude a little bit. And then it will, you'll see that really your catchment is really biased, is not 0. But that's a very good point you made.
Okay. Thank you, sir.
Any other question? So this was developed by me and Dr. Khaled Haddad from our university, this project. And really, I think this is one of the most important tools that we have developed in our career, that people are using it quite a lot. And this software has been used over 10,000 times in the last 5 years or so. So this is a very good software in our opinion, and it really has a lot of the things it has considered. And it was developed after 10 years of research. We did a lot of research for 10 years. And then we have implemented, we have put everything in the software so that people can apply it. Okay, I think so that's all probably for this tutorial class. I think there is no other question but I wanted it to show you the Brewer Metallurgy website. So let me show that one. And another thing is that you can go for advanced technique. So if you want to go to advanced one, so let us go to the, and in this technique, you can see there are about is really this how this technique was developed and what are how many data points used, and really who are the acknowledged person who worked in the team. It's a big team of project people are there. What are the limitations of these techniques are here? What are the key publications that if you want to do more about this method? And finally, the acknowledgement is here, and change log is here, that really if we are doing any changes, then we put it here, that what are the changes we are making. You see that it started in 2015, and then in 2016, we made some changes there. So now if you want to go apply this advanced technique, then what will happen is that, so in advanced technique, you have to really put your rainfall intensity values, which you have to obtain it from Australian Brewer Metallurgy website by yourself. And then you will be able to get the estimation. So I'll show how to get the values from Australian Brewer Metallurgy website. So I'll stop share here. Okay, so I will be going to the Australian Brewer Metallurgy website. Give me a second. So can you see this screen that if you type BOM, can you see this screen? Ali Ahmad?
Yes, we can.
Yes, we can see.
So you click on BOM and then you type here enter search item.ifd because this rainfall is called intensity, frequency, duration rainfall, IFD. So if you say IFD, which is the intensity, frequency, duration data of design rainfall, and then if you say search, then you will see still the 1987 IFDs are there, which is the old version. And then, so this is there are many different sites and there are many different things. So basically, like I think it's going this on here. So this is the website that really you use for estimation of the design rainfall at any location. So I'll show you some example that if you click here, then it will give you a window that you can do it for single point. So I go for single point. You can do it for multiple points. So latitude and longitude, we have to give the centroid latitude and longitude. In this case, it was our minus 30.352. And longitude was 151.936. Is that right? So it's in decimal degree. So level, you can say our site 1 or something, whatever you want to say. Site 1, and then if you say submit. Then it will show you the right location where it is. And then you can get your unit in millimeter per hour or millimeter. There are 2 units here, but millimeter per hour is needed for our method. And for different duration, you have the different intensity for different return period. So you see that for this one is for most frequent rainfall, like it's had like exceedance per year, which is estimated by the partial duration series. So basically, we have selected very frequent, which are the estimation needed for environmental flow analysis. But for IFD, which is the frequent and infrequent, which is really starting from 2-year return period to up to say 200 or something, 500. So let us see what we get. So you see now we have got 1% AEP, which is 100-year return period. And in this method, we use 6-hour duration. So 6-hour duration and 2% AEP. So basically 6.92, that is the value we have used there in our estimation. And then really you can specify particular duration if you like. And also you can go for real rainfall as well. And if you say go to real rainfall, then you see it's giving up to your 100-year return period to 2000-year return period for different duration. So our Western Sydney University, we assisted Australian Bureau of Meteorology as well in deriving this IFD data as well. So they gave us some funding, and Khaled and me, we developed some technique for them to do the GLS regression for doing the estimation at all different locations. So any question? No question? Okay, Saika, can you take the attendance now?
I already did, Professor.
Gokan, sorry.
Yeah,
Gokan,
it's
have you
alright.
taken the attendance?
Yeah.
Okay.
All good.
Okay, so Gokan, do you want to say anything to the student?
Not at the moment. You put in.
At least probably show your
Send everything.
picture and introduce yourself with the student.
Yeah, sure. I don't know the students can. Yeah, I can introduce myself. I'm doing my PhD. I'm working on the.
Could you please speak louder, please?
Sorry, sure, of course. My topic is drought assessment in Southeast Australia. We aim to publish 4 journal papers from my thesis. And actually, I submitted recently my thesis, and we are waiting for the comments. But I will continue my studies with Professor Rahman. And in this unit, I'm helping students and I'm moderating this unit. And last year, I was giving tutorial, but after COVID, we were not able to do that. So that's why the Professor Rahman doing tutorial this year. Yeah, that's all.
So I think thanks, Gokan. I think Gokan was probably you have seen him in some of the subjects in fluid mechanics.
Yeah.
And in other subjects, particularly in laboratory of the fluid mechanics, he has been taking that class for the last 3-4 years. So you might have met him before. And so Gokan and Saika, they are our tutors and examiners in this subject. If you have any question or anything, then you can ask them or to me. If you don't understand anything particularly, then you have to ask question to us. Otherwise, we don't know that what you have understood or you have not understood. Once you come up with the question, then we can answer it. Otherwise, we assume that you have understood everything. Okay, is there what about my PhD student who are present here today? Is Ali Ahmad here? I can see. Is Amir here?
Yes, sir.
Amir?
Yes, sir. Ali Ahmed is here, sir.
Ali Ahmed. Gokan, can you note down the PhD students? Ali Ahmed, put the name there,
Yeah,
Ali Ahmed.
Yeah, I did. I marked everyone in the participant list.
I can see Nilufa is here.
I missed that.
Nilufa is there. I can see who else? Our PhD student here. Only Ali Ahmad and Nilufa, is that right?
Orpita was here.
Orpita is here, is that right?
Yeah.
And what about Amir and Abu Huraira and
Abu Huraira was here. I don't know at the moment he's here or not.
I can
But
see.
he joined it, yeah. I can't
But
see
why
him,
Amir
but
is not
joined.
here? Because Amir is doing PhD on this topic.
I don't know. Amir didn't join the last
Time as well.
last
So
session. Yeah.
he's trying to become smart.
I think
or something.
pretty is not coming too. So
Anyway, because it will be recorded and it will be put on the YouTube anyway, so they can watch from YouTube. And at the same time from the views as well, the other students. So I think that's all. If is there anybody has any question on this? Okay, so I think then in that case, probably we'll close the class here. Thank you, everybody.
So what about attendance?
Attendance has been taken,
I did
recorded by
attendance.
looking at your participation in the views.
okay, yeah. Let me explain how I'm doing that. I'm checking the participant list frequently. Every 5 minutes, I'm checking because sometimes student join, leaving, student join, leaving.
No.
And if I don't find the name, I'm asking student privately. I'm asking the student number.
Thank you.
Okay, no worries. So everyone mark as attended. No worries. Okay.
Okay, so I think if you don't have any questions, then we'll close the session here, and I'll stop recording first. And then I think Gokhan and Saika, you have a meeting, is that right?
That's correct. Yeah.
So I'll stop recording first, and then we'll continue our meeting. Stop. First we say stop recording, I guess.